to our second speaker. Thank you very much again, Regina.
Thank you.
So our second speaker who's joining me on screen is Jeffrey Mitchell from the Department of Psychology of the University of Bristol in the lab of Jeffrey Bowers. And he'll present us his work on spatial symmetry and its relation to grammatical structures. So please, Jeffrey, you can share.
Thank you. Yeah, so this is a talk about the relationship between spatial structures and grammatical structures. So the linking idea here is symmetry. So spatial symmetry is an important constraint in neural architectures, particularly to do with vision. It's been enormously useful in helping us recognize pictures of dogs, mainly. And so the important thing about spatial symmetry is that given a dog in one position in the training set, we are able to generalize to the same picture of a dog anywhere else at test time. So this has been an enormously important constraint on the architectures that people have looked at in deep learning. But what I want to suggest is that this is also enormously useful in thinking about symbolic systems. In particular, we can apply spatial symmetries to the memory structures that symbolic systems work with. So not only will spatial symmetry help us deal with external input in the form of images, but also help us structure our internal representations in terms of memory. So just to motivate this, I've got an example sentence: the barmaid that John's extremely obnoxious friend offended refuses to serve us. So when you're processing this sentence, what you want to pick out of the sentence is who did what to who offended who, and who refuses to serve us. So this is a relationship syntactically between nouns and verbs. And recently, neural language models have become extremely effective at processing such sentences and extracting this who did what to whom information from them. Lecretz et al. Looked at how these syntactic dependencies between nouns and verbs were represented within a neural language model. And what they found was that short range of dependencies, such as between friend and offended, were represented in a separate unit from the long range dependencies, say between barmaid and refuses. So this is a problem because really these are the same dependency between, syntactically they're the same between a noun and a verb, and you want to represent them in the same way. So what we're going to do is suggest that you can use a symmetry to connect these short range and long range dependencies. Just as you can learn that a dog is the same wherever it is in an image, you can use symmetry to learn that a short range dependency is the same as a long range dependency. So just thinking in a bit more detail about that sentence and how you process it psychologically, what would happen is that you hear the barmaid and you think, well, what did the barmaid do? So you need a verb phrase. Then you hear that, so you know there's some extra information about the barmaid. There's a relative clause. The barmaid that did something else. So you need two verb phrases. But now you get John's. You need to know what belongs to John. Is it a hat or a leg? And instead of a noun, you now get an adverb. So you need an adjective to go with that adverb. So extremely tall or extremely short. So you need an adjective next. So we've built up these expectations about what we expect to happen in the sentence. And what's going to happen next is that we fulfill these expectations in reverse order. So we're going to get a last in, first out structure. So the last expectation was adjective, and that's going to come first. So we say it's extremely obnoxious. We then say it's John's friend. What did the friend do? He offended the barmaid. What did the barmaid do? She refuses to serve. And that's why we get these short range and long range dependencies, because they become nested as we do this backwards recall. So linguists have thought about what sort of computational machinery you need to process this. And in particular, they've also been interested in what sort of constraints do you want to impose on your computing machinery in order to account for natural languages. And generally speaking, they've gone for context-free languages. There is a hierarchy with Turing machines at the top and finite automata at the bottom. But generally speaking, when we talk about language, we're thinking about context-free grammars and push-down automata. So here's an example, a really simple example of a context-free language. We've got 5 symbols, A, B, C, D, and O. And each sentence in the language is a palindrome. It's the same forward as it is backwards, with an O in the middle. And so for each A in the first half of the sentence, there's a matching A in the second half. The same with B, D, C, and A. And so we get these long-range dependencies and also short-range dependencies, and they behave very like the dependencies between nouns and verbs. So we're going to use this toy grammar to explore context-free grammars rather than the full grammar of English, because that's a lot more complex. So in terms of a symbolic machinery for processing such a language, this would typically be a push-down automata. And what this is, it's a controller that reads and writes from the input, and it has a push-down stack, which is a last-in, first-out memory structure, which it writes to. So it's here in the middle of the palindrome, and it's read A, C, D, B, A, and it's written that to its stack. And it's now going to read it out in reverse in much the same way as we saw with the barmaid example. So A, B, D, C, A. So that's a symbolic architecture, but I'm more interested in the neural architectures. So neural architectures are very similar. The main difference being that the memory here has no structure. It's just a set of hidden units that the neural language model can use however it pleases. And in particular, one of the popular architectures is an LSTM. And basically that has 3 types of gate: an input gate that writes to the hidden units, an output gate that reads from the hidden units, and a forget gate that essentially controls the recurrence. It controls what is held in memory and what is forgotten. So if we take this LSTM, we can train it on some language data. Here's some data from that palindrome language. We have medium length training sequences, and then we have some out of domain test with much longer range dependencies in them. So if we train our LSTM on that data and test in domain, that is on sequences of the same length, we'll get 100% generalization to that in domain test set. If we now try to generalize to much longer sequences where the dependencies are much longer, we haven't seen that before, our performance falls off very sharply. We no longer generalize. And like I say, this is because there isn't a connection between short range and long range dependencies. And so what we want to do is to make that connection via asymmetry. So in much the same way that you say a dog on the left is the same as a dog on the right, doesn't matter which position it's in, we want to say the same thing about these dependencies. It doesn't matter if it's a short range one or a long range one. So we'll take our neural memory, our neural language model, our LSTM, and in order to structure those hidden units, what we want to do is impose a symmetry so that every range of dependencies within those hidden units is treated in the same way. It turns out we can do that simply by replacing the forget gate with a convolution. So the same convolution that we use in image processing, we can impose on our hidden units, and it turns the hidden units into a push-down stack. They now have a spatial structure, they have an adjacency, and we can push things up and down the stack in exactly the way we need. And so it's not surprising that when we train such a model on the language, you now get perfect generalization to the long range dependencies. So that points out that there is this connection. There is some sort of connection between spatial symmetry in image processing and context-free grammars. So the constraints that people have been looking at in terms of neural architectures turn out to be very similar to the constraints that people have talked about in terms of context-free grammars. So this work is related to a number of other investigations. On the symbolic side, a number of people who are interested in the grammar of languages have looked at the relation between planning and navigation and symbolic grammars. People who are interested in how planning and navigation happens in the hippocampus have also been interested in looking at how those spatial representations relate to more abstract conceptual knowledge. So our work is kind of sitting in the middle, saying, you know, the bridging connection possibly is this idea of symmetry. So thanks for listening. I look forward to some feedback.
Thank you very much. Very interesting. And personally, I study like semantics, like high-level language. So my mind was immediately going towards the grid-like code for concepts. Like it resonated with me. Maybe sort of a naive question just to start. Do you have any data or any insight, or are you planning to explore how this would actually work with English, like with a real language, with grammar in a real language?
So that's a good question. I mean, so I'm not the only person looking at these stack-like recurrent models, and people have found that there may be advantages in terms of uncovering the syntactic structure, the syntactic trees within languages like English using a stack structure. The trouble is that natural languages are really complex, you know. There's all sorts of things beyond context-free grammars, even beyond syntax. There are, you know, semantics is a very important, and that introduces dependencies that can be very diverse and tangled. There are parts of language that are not compositional. They are just, they don't really have an internal structure. So all these things conspire to make these models difficult to train. There is, of course, the issue that maybe back propagation isn't the best way to train these models anyway. So even on this simple toy grammar, the training is quite often non-robust. It quite often goes off and does something crazy that I don't want it to do.
Right. There are always too many things that are covary in natural languages, right? Like to disentangle one thing from another then becomes virtually impossible. So what is the direction you're thinking of taking? Like, what's the next step? Do you think there's another principle, another spatial principle on top of symmetry that you could inject in the model, or?
There's various things I've been thinking about. So making the training of these stack architectures a bit more stable, that would be useful. Bringing more semantics into it. So at the moment, it's really just a connection between context-free grammars and symmetry. And as you mentioned, you know, semantics is an important part. So we have to think about how that fits into the model. And in particular, how it fits into the model without deteriorating the syntactic part of the model, which is complicated in itself. So that there's a few directions to go in.
Absolutely, very interesting. I don't know if we want to have both speakers